Hello again. This is the second class in the high school chemistry series. Apologies for the delay, there are some technical issues, but now we're ready to get started. So today we're going to be talking about Lewis structures and the shape and geometry of molecules. Also, on a related note, we're going to be touching on IMFs, which are intermolecular forces, since they're particularly relevant to this topic. Okay, so firstly, let's sort of recap what a molecule is. And this chart is just sort of like a little preview. So let's look at molecules. So a molecule is defined as a group of two or more atoms chemically bonded together to form a neutral particle. They're usually, the neutral part is sort of important in that the molecule is not an ion and it doesn't have a charge. So it's sort of different from ions. But there are ions that are formed by a group of atoms, and they're going to be called polyatomic ions. You'll probably come across some of them in the near future of your chemistry studies. So since they're sort of free-floating particles, like when we say molecules, we usually refer to liquids and gases because the molecules are able to move around and they're independent particles. They usually form through covalent bonds, which is two atoms bonding by sharing electrons to fill in their respective shells. So they're not usually ionic or metallic bonds because those are usually found in solid substances. For example, ionic structures, since they're formed by formal charges, they tend to form like a lattice or a crystal structure. And metallic bonds are sort of a very specific kind of bond because they usually they're described with the phrase protons in a sea of electrons, which is sort of true because as we know, metals are usually on the left side of the periodic table, and therefore they have a low Z effective energy, which we talked about last time, and a probably very large atomic radius. This means that they're not very good at holding onto electrons, and therefore in a metal solid, electrons are sort of free-floating because they're not bound very tightly to anything, not very tightly to a proton. And therefore, without ionic or metallic bonds, molecules are usually formed by nonmetals bonded to each other. Okay, so now that we sort of talked a bit about molecules, let's sort of jump to Lewis structures. Okay, so today we're going to be using a textbook called Introductory Chemistry. We can link it somewhere if we need, or you guys would like to see it, but for right now we're just going to use it for reference. So we're going to go to page 425 and just slightly review the bonds a little bit. Okay. Okay. Well, I hope you can see most of that at least. Yeah. Okay. Good thing it has large margins. So we're going to be talking a bit about Lewis dot diagrams first. So a Lewis electron dot diagram, or it's usually abbreviated as Lewis diagram or Lewis structure, is a representation of the valence electrons of an atom that uses dots around the symbol of an element. So that's just mostly a description of how it actually looks. So you see this is sort of like a diagram of hydrogen. It has one valence electron, and you can put the valence electron anywhere, basically. And that's just representing that it has one valence electron. It's almost sort of like a visual representation of an atom, in the way that it has like the electrons surrounding the central like nucleus. So these are just some more electron diagrams. And as you see here, it's made so that the Lewis diagram is sort of made so 8 electrons fills a shell. So you have 2 on each side and 4 sides, and you fill in the valence shell for at least the first 2 rows. Okay. So in the book, please excuse the excessive scrolling, it talks a bit about covalent bonding in a little more detail. This is also ionic bonds. So if you would like us to cover this in more detail, please feel free to comment or request such a breakdown, and we will try to do that. So, but for now, I think we're just going to dive straight into sort of talking about covalent bonds, because they're pretty essential to Lewis structures, as Lewis structures are for molecules, as well as other things, but we mostly use them to sort of look at how like molecules are formed and what their structure really looks like, whereas in ionic and metallic bonds, usually the structure is a little more clear. So we're going to focus on covalent bonds, basically. So as I previously mentioned, covalent bonds are sort of a mechanism for obtaining a complete valence shell for the atom, which is achieved through sharing electrons. And what this sort of means is like this idea of sharing an electron is kind of a finicky thing. So if the 2 atoms, or like the nucleus of the 2 atoms, get close enough together, they sort of mutually attract electrons from each other, and that's sort of what creates like the sharing effect, because the electrons belong to both of them technically, because they're both in sort of the radius of one and the other. Alright. So the point of covalent bonds, or any bond in general, is to try and lower the sort of potential energy of the atom, and in that sense, sort of making it in the most stable state possible. And in order to have a stable state, it probably doesn't want to be very reactive, and therefore it needs full valence shells. So in this case, we look at this example of hydrogen, or H2, that in the way that it's bonded, and we see that it has each H now has 2 electrons. So it completely fills the atom's valence shell, because H is in the first row of the periodic table, and it only needs 2 electrons to fill its valence shell. So there are a couple sort of bonds that we should talk about. I guess it's not really sort of like laid out for us here, but this kind of bond with just a single electron pair is called a single bond. Now, with atoms like oxygen, diatomic oxygen, molecules like diatomic oxygen and diatomic nitrogen, you'll see double and triple bonds being formed, which means that there are either 2 or 3 electron pairs shared between atoms. But we'll get to that a little later. So this is them demonstrating a fluorine atom. And yeah, they're sort of just telling you how this diagram just sort of shows like how you're going to be sharing the the electrons with the different atoms. So, let's take a look at how we actually draw these diagrams, which is sort of explained here, talking about the steps for determining a Lewis electron dot diagram of a simple molecule. So this is where we're going to get a pen and start kind of drawing. So the center, there are sort of like parts to this diagram drawing thing, like a sequence as they're going to say, but first you start with the central atom. So it's the atom in the center of the molecules, and and usually there are certain rules you have to follow with it. For example, it needs to have more than one bonding site, or like be able to form more than one bond usually, because it needs to be able to connect all the other sort of molecules together, or like through itself. So it should be able to form multiple bonds, but also it should not be very the most electronegative. We'll probably get to this a little later when we are actually drawing it and we can apply it. So let's just continue with the steps for now. So, oh yes, the central atom is usually written first in the formula of a compound. In my experience, I've always just sort of determined it by drawing, but sometimes that will be the case. And as you can see, here it says H2O is a notable exception. That is true because H can only form one other bond with another molecule, or can only share one electron pair with another molecule before it fills its valence shell. So in this case, oxygen would actually be the central atom. So after you've identified the central and surrounding atoms, you have to follow a series of steps. So valence electrons are very important in being able to draw molecular structures. So first, you would need to count the number of valence electrons. And that is true. If the species has a negative charge or a positive charge, in that case, if it's a polyatomic ion, then you would need to sort of accommodate for that as well. Usually, if atoms sort of have an extra negative charge, we will draw it, we will draw it with an extra electron quote-unquote pair, but then we'll account for it in the end when we we talk about the overall charge of the molecule. I mean, the ion in that case. So you would need to count the total number of valence electrons, and it is very convenient actually to write not only the number of electrons, but also the number of electron pairs, which in that are the sort of things you'll be using to draw them. And it's also useful for determining other things. So then you would write the central atom and the surrounding atoms around it. And you would first try to connect all the surrounding atoms to the central atom, because they must be connected somehow. And then when you have extra bonds, complete the octet around surrounding atoms first. And when you have electrons remaining, put it back on put them around the central atom, and then check that every atom has a full valence shell. So this is sometimes where double bonds and triple bonds come in, because sometimes there's not enough for all the atoms to sort of have like single bonds, and you have to share 4 electrons instead of 2, or 6 electrons. So I say we try an example. How about we just go for one of them on the book? Actually, let's not do that. We can try the electron diagram for CO. Actually, you've already seen it, so let's just use maybe one of the practice problems. Okay, so how about let's take a look at H2S. Well, let's go on the canvas, or Microsoft Paint in this case. Oop. There's a periodic table on it, conveniently, I guess. Okay, so let's just try to find some, not draw in the periodic table. Here's a bit of empty space. Alright, so first let's think about the steps. So, okay. First we want to sort of identify the atoms involved, so of course in H2S, we have an H, or two H's, and an S. And H has one valence electron, as we've sort of discovered, and sulfur, since it's in the oxygen family, has 6 valence electrons. Let's just double check that real quick, just in case. Okay, as we see, sulfur is right there, and 16 minus 10 is 6, so it does actually have 6 valence electrons. Okay, let's continue. Okay. That is a very bad 6. Okay, so let's follow the steps. So as we were talking about before, first you would count the total number of valence electrons. So we've already sort of found how many each of these atoms has individually. Now we just have to add them together. So 2 hydrogens each have 1 valence electron, and you add the 6 valence electrons of sulfur and you get 8 total electrons. But you have 4 electron pairs. Oh lordy lord. Writing is very difficult. Alright, well we'll just leave it at that for now. So then we say, write the central atom with its surrounding atoms. So in this case, we have sort of the same situation as H2O, where the first atom written isn't the central atom, because it can only form one bond. So therefore, the central atom is sulfur, going to be sulfur. And then H and H are the surrounding atoms. So we have 4 electron pairs we can use, and we know that we need to connect hydrogen with sulfur. So we're just gonna sort of draw a line. Technically, you can also use dots. Let's just draw another one down here with dots. I guess it's easier to see with dots if you have sort of like an odd number of electrons, which sometimes happens. But I sort of like to use lines more because that just makes a little more sense to me in terms of bonding. But you can of course, for sure use dots. So that's that. And then, well, now H and H have completed their octets, or not octets, but their full valence shells. So now we can put the 2 remaining electron pairs around the sulfur atom. And that's sort of like our completed preliminary diagram of H2S. Yep. And does every atom have a full valence shell? Yes, it does, because S now has 4 electron pairs, which are 8 electrons, and it formed a full octet, and therefore it's satisfied. Alright, so there are some things we can do with this, multiple things. And two of the most important, or sort of not most important, but two of the important describing factors of a molecule are the geometry and shape. So let's take a look back at the lesson plan. Bye for now. So what determines the geometry of a molecule? Well, the steric number is basically the name of the number, the name given to the number of electron pairs that surround the central atom. So, this is where we sort of get to use the chart that we looked at earlier. I'm just going to go a little over because we started really late. So here are some basic sort of geometries. It goes actually all the way to an element that has 6 sort of electron pairs surrounding the center, which gives it a steric number of 6. I'm not sure if you guys will get to that in regular chemistry just yet, because it's a little bit difficult. Yeah, but if you do get to it, it's called octahedral. So, the geometry is called octahedral. Yep. So, let's take a look at how many valence electron pairs are surrounding the central atom. And as you can see, there are 4 total electron pairs surrounding. So if we sort of look down this chart, the steric number for H2S is going to be 4. And here you can see that means the geometry is tetrahedral. Now also note that on this chart it says basic geometry, and also underneath 0 lone pair. Now that is not exactly the case with H2S, and we'll talk about that in just a second. So it has a steric number of 4, therefore its geometry, oh my goodness, okay, its geometry, please bear with me here. I'm just going to write geo for short, is tetra. Oh my. Wow, I'm really sorry about the stylus. Tetrahedral. And you may recognize the tetra prefix, which is sort of 4. Yep. So, its geometry is tetrahedral, but that is not what its shape is. And the reason being, there are lone pairs. Now, if you continue to look on this chart, and you go down and sort of look at how many lone pairs there are, well, in this case, there are 2 lone pairs. Oop. Let's change the color for fun. Right here. So, the shape will actually be bent or angular, as it's called. So let's just write shape down below. Zoom in so we can get the best writing quality. The shape will be bent. I haven't exactly heard anyone use angular before, but usually we say bent. I'm assuming both are okay. And yeah, also if you can see a little bit on this chart. I'm not sure how blurry it'll be, but there are also angle measures that are on there. So I'm just going to talk about that really quickly. So I'm going to talk about it up to tetrahedral because I think that is most likely what you'll be studying until. But for a linear molecule, okay, so there's sort of a theory behind this, and it's called VESPER. Well, not exactly, but VESPER is an acronym for this theory. Right here. Valence shell electron pair repulsion theory, or VESPER theory, is a model used in chemistry to predict the geometry of individual molecules from the number of electron pairs surrounding their central atom. So this is sort of related to like the steric number, the whole steric number idea, but it's basically saying that the valence shell pairs want to repel each other as much as possible. They want to get the atoms they're attached to sort of like as far away as they can from their other electron pairs, because as you know, electrons have negative charge, and negatives sort of repel each other. Two negative charges repel each other. So in order to sort of get those like things as far apart as possible, you sort of have to take a look at the shapes again. So the geometry sort of, yeah. So we can think of these sort of like atoms maybe as like building blocks. So I'm just gonna sort of draw circles or some other shape because writing is difficult. So a linear molecule, as you can see on the document, let's just draw this out. The farthest you can get two things apart will be sort of at a 180 degree angle. You have them sort of flat and opposite from each other, and that's the farthest you can get them apart. But what about three things? Well, I'm just going to draw circles. This is difficult. Okay, three things. Well, if you think about it as like flat on a circle, sort of see that if you divide 360 degrees in a circle by 3, you get 120 degrees. Oh, okay. 120 degrees. And that's that's the maximum distance you can get these three things from each other. Now what about four things? Well, that gets slightly more complicated. At school, we tried to sort of manipulate it on the plan, but it's definitely a lot easier to use like 3D models and stuff to see how far you can actually get these things apart from each other. And we ended up with a shape that was kind of like, I don't know, a WALL-E or like a Mars. I don't know. It was just like it was a fully standing object, sort of, with like sort of a pyramid shape at the bottom, and then, oh, that is most definitely 5 things. Oh, no, just kidding. It's 5 things, sorry. There are 4 bonds. My bad. So basically, we figure out that this this distance is actually 109 degrees. This angle measure, and that's the farthest. Some people say 109.5, but that's the farthest you can get 4 things away from each other, surrounding like a central loci. And another thing that you might notice is that with each addition of a lone pair, the angle measure gets smaller. So if, for example, in the trigonal shape, this were to be a lone pair, this were not to exist, and there were 2 electrons here, then these 2 electrons would push these out, and then this degree would end up being smaller than 120 degrees. Same thing here. Like if one of these turned into a lone pair, then this angle would be smaller than 109 degrees. Oh, okay. So why is that? Well, we'll look back again at the VSEPR theory and notice that electrons want to be as far away from each other as possible. Well, lone pairs, if they're attached to an atom, they sort of take up less space. I mean electrons, because aren't they being pulled in by the atom itself? Well, yeah, I think without the atom sort of like pulling the electron towards it, you just sort of have like two free floating like dots over here, and they're going to want to spread out as much as they can. So they end up taking up a lot more space than an actual atom, which is kind of odd, but that's the way it works. So it pushes these like sort of pairs like back in, like they're getting scrunched. So that's why, just like remember that lone pairs always take up more space than an actual sort of atom does. Okay, I'm not exactly sure if we will have time to really go pretty in depth into molecular structure and IMFs and their relation. So I think I might just want to talk about how to draw a 3D model then. Let's do that. So one of the important things about a 3D model is that it actually gives you sort of a visual like look at how the molecule is. So you'll be able to you'll be able to really tell like if some structural things about the atom. For example, its symmetry, or where exactly the lone pairs are. Because if you just sort of write it down on paper, like we first did with the H2S atom, you might think that it's actually straight. Like one way we could have drawn it was like this. And we could have just drawn the lone pairs like that. And it's actually not, it doesn't actually have lone pairs. It's just like, it's not asymmetrical. It just has lone pairs on both sides. That's how it works, right? No, it actually does not work like that. And if we said this shape was linear, we would be wrong. So let's just try drawing a 3D model. Let's just use H2S as an example. That's a 2. So in drawing a 3D model, we sort of want to consider the shape and geometry, as we've said just a couple minutes ago, and you want to also look at the angle a little bit. So in this case, if you sort of ascribe this drawing to the diagram, a bent molecule is actually kind of like a little bit easier to draw because there's only like 2 things. But if you have like a tetrahedral molecule with like 4 atoms attached to the central atom, sometimes it's a little bit difficult because you have to remember to shade and like draw those weird lines and stuff. And technically here you could do the same thing. So let's actually just try that. So we know that this atom has 2 lone pairs, and the lone pairs are going to take up a lot of space. So we're going to put them at the top here. You can technically draw them with dots, but in this case, in this diagram that they show us, they actually draw it like this. So one thing that's sort of interesting about this is that even though it's poorly illustrated by me right now, these sort of triangle things are supposed to indicate like shadows. It's supposed to make it look more realistic. So any of you artists out there, it's supposed to be realistic to some degree. So here are the lone pairs that are sort of shown. And since this is a bent tetrahedral molecule, we look at the chart and we see that this angle is a lot smaller than 109, is what they're trying to say, I think. No, but this angle is going to be a lot smaller. By how much, it sort of depends, but it is going to be smaller. And sometimes you're asked that. So the lone pairs are kind of sticking up on top here. And sort of with the last couple minutes left, I wanted to talk quickly about polarity. So sometimes you hear the word like molecule is polar or non-polar being thrown around. And take a look at the notes. Let's just ignore the IMFs stuff now, but if you already know that, that's super awesome. Totally great. So polarity is usually indicated by sort of the symmetry, like the symmetry of the molecule. Ooh, eraser. Okay, we can erase these weird dots now. So, and what we sort of mean by symmetry is like, oh my goodness, they're reappearing. That's okay, whatever. Is sort of like how the charges balance out more than how the atom actually looks. So in this case, this sort of this diagram of H2S sort of looks similar. I mean, symmetrical. It has two, however, it has two lone pairs, like sort of on the top here, and two H's down here. And the charges, however, are not similar. The charges are, the charges are not symmetrical. And the reason being, the lone pairs are sort of gathering at this side of the S. So the lone pairs are here, and that means that a lot of the negative charge is being drawn over here by these electrons. So this side will be highly negative. It'll have sort of like a partial negative charge. Whereas on this side, since electronegativity, we do need to mention that. So electronegativity, as we sort of mentioned in the past video of periodic trends, is how likely, or how sort of like how much an atom can take an electron from another atom, or like how attractive is the atom for electrons. Well, in this case, sulfur is going to be a lot more electronegative than than hydrogen, sorry. And that's because it's on the right side of the periodic table, and it needs just two more electrons to fill its valence shell. And it's got a higher Zeph, at least in comparison to H. So, if this is going to be a very electronegative atom, and it's going to attract electrons, then the electron, even though it's being shared, it's going to stick to this side of it a lot more. These little dots. So the H is going to end up having almost like a little bit of a positive charge, because of how attractive, how there's a difference in electronegativity between sulfur and H. So this side is going to have slightly positive charge. And if we look at the whole picture, this side is going to sort of be a negative pole, and this is going to be a positive. So sort of the direction of polarity is going to be this way. The plus sign just kind of became part of the arrow. So yeah, and that is sort of going to be its polar, its sort of permanent dipole, which means that this side would usually have like a negative charge, and this side would usually have a positive charge, like sort of permanently. And if this is something that is difficult, we can try to explain this in the next video, talking about IMFs. We may combine that sort of with gas laws, because those two are also really related and really relevant. So I think we're just going to end this lesson here. Yeah, please feel free to comment if you have any questions or suggestions. And thanks for watching this stream.